Welcome back to however many we had so far, and last first meetup. Um, the gentleman who goes under the name Code Doctor in our Slack suggested a topic, I think last week, which is exactly once. I have no idea how to best introduce us to this topic, but exactly once is actually an industry standard term that stands in between at least once and at most once. It has to do with messages delivery via some message brokers, pipelines, or whatnot. And the essential part is that, as it turns out, at least once, as in you can resend stuff as necessary, is super simple. You just have some resend logic. At most once, as in you need to make sure that the message is not sent more than once, is also kind of easy. Ever since the message has some logic to not send it again. Exactly once, which sounds simple, is a super non-straightforward problem. It borders with everything. It borders with the gap theorem. It borders with microservices architecture and monolithic architecture. It borders with data consistency and just being sure you can store the data reliably. So sounds plausible, extremely hard to do right. Good thing is it actually has some techniques and tricks that make it kind of easy to work with. And again, part of the goal of my meetup is some education with respect to making sure you can speak professionally and get your job done well. So there are a few simple things you can learn within, well, I would say the next 40-ish minutes, which should help you with this. With no further delay, I'm going to share my screen with the slides. How do I move this guy? Anyways, it's going to stay here. So, what we're talking about here is that you have a service with multiple components talking to one another. One of the industry standard terms, it's kind of fluctuating these days, to be honest. The most commonly used term changes here and there, but for the at most one's delivery, one of the most commonly used terms today is fire and forget. You may have heard it before. It's that you have the message, you just fire it out, and you forget about it. I don't think there is a standard term for at least once, but basically on a conceptual level, at least once means until we have a confirmation that the message went through, we will try to resend it. Like again, logically speaking, these are strict guarantees, right? So if you have multiple hops which the message has to go through, if at least one of the hops dares to resend the message in case of no confirmation, then you can non-guarantee the message is not delivered more than once. At the same time, if at least one step can drop the message, you can non-guarantee this system is at least once. So it's kind of tricky. If you need to make mistakes in one direction only, you can make sure every single component only makes mistakes in this direction. If you need exactly once, and you have multiple steps along the way, you have to make sure every single step is covered. Skipping forward a bit, if you have two systems, A and B, and let's say there's Kafka in between, which is a kind of standard way to make sure you have the message queue that is persistent. You would say that Kafka itself kind of tries to give you the exactly once guarantee. You can rely on it, but you have some application server that writes into Kafka and something on the other end that reads from it, each of which you can mess it up in different ways. So just be careful with that. Just making sure you're only using the components that guarantee exactly once delivery doesn't guarantee anything. So sometimes we do not really have the problem. Sometimes what we have is a system where it's perfectly fine to lose some events, especially if those events are not too many. Obvious examples would be weblogin. Something like Google Analytics, well, there's zero downside to having 0.something% of messages lost. There's literally no issue whatsoever. even unless you have some super advanced funnels that you need to analyze with Google Analytics that only one person in multiple million goes through, unless you have this degree of precision requirement, you can just assume that some messages will be lost. And if you do have this degree of precision required, chances are you would probably use your own trackit with client-side retransmission, business logic, on-device, etc., etc. Sometimes you have communication where keeping low latency is more important than delivering everything. So, like the layman recommendation would be if you can choose UDP over TCP, chances are you're looking at most once delivery. So, for example, if it's a video call, there's no reason for you to resend the frames that were not sent. If your network connection had a gap of a split second and a few frames were lost, you better use the bandwidth you have right now to work with the up-to-date image and sound, as opposed to trying to resend stuff from the backlog and vice versa. And one good example is sometimes the APIs are structured in a way that allows for messages to be lost. I'm not sure it's a good example overall, but it's a good example to explain. When you trade in stocks, the interface is you take your device, you would like to get a quote, you request a quote for some ticker, and you get back to the price. Well, bid and ask, price, buy and sell price. After you got this bid and ask, you can make a trade the next couple of seconds at the prices that were quoted to you. If you ask for a price and the request times out, I wouldn't say it's desirable, but there is no harm done. You just re-request again. That's an example of a kind of an API where it's perfectly fine to lose messages sometimes. And again, if you place a trade, there's an order ID. So again, we'll get back to this in a while, but there's no real harm done. And sometimes your system is designed in the opposite way. Sometimes by design, there's no harm in messages being delivered more than once. I work in the real-time gambling industry, so sometimes there's something like, well, I can even make a stronger statement. One of the challenges is to broadcast messages everywhere. So if millions of people have some table open, a lobby open, and there's some number there, like how many people are online, what's the score of the current match, how many players are left on the final poker table, this is being broadcast. So once the number changes, everybody should see it. That's a hard problem, but at the same time, if an update goes out every few seconds or even more frequently, if you miss an update, there's no big deal. If you get that update twice, there's no big deal. And of course, one of the most important techniques that allow you to not worry about exactly once delivery is what is called idempotency. Idempotency is the idea that, well, it's not even the idea, it's the philosophy of designing the API in a way that gives the user of the API the guarantee that the same requests would always get the same responses. That sounds weird, because if you're looking at, let's say, a Facebook post, and it shows you a number of likes, there's a good chance this number of likes would change if you make the same GET request an hour from now. Or maybe the post privacy settings were changed, or maybe the post was edited. But it's not hard to imagine that you can design the API in a way that would always give you the same response. For example, you could ask, how would this piece of content look like at a certain timestamp? If it's a timestamp in the past, then you can imagine it's frozen. Again, you would have to worry about privacy, etc. If the post is deleted, you probably don't want to respect the guarantee of sending the same data to the user. Maybe some credit card or address were compromised there. But fundamentally, you can design the API so that the same request gives the same response. It's not really interesting to talk about this API guarantee when it comes to GET requests, when it comes to non-mutating requests, when it comes to the requests that are mutating. So not GET or HEAD, but POST or PUT. So you change something or delete something. It sounds weird on the one hand, that you would like to, let's say, make a financial transaction. You would like to pay somebody. I'm paying my landlord, I'm opening my application and clicking the button to send money. On the one hand, it's weird that if you click this button again,
the money is not reset. But on the other hand, if the API call to make this request has some token within it, some huge random-ish, we'll get to this soon, but if it's some huge unique number or string, and the convention is that once you make the request and it's successful, the response you get back is request successful. Request with this ID is successful. You can make a new GET request, a no mutation request, and ask for the status of this response. You will get something like response was received, or the request was received. You move the timestamp of your request further into the future, and you can get it succeeded or failed. But fundamentally, it doesn't matter how many times do you send this transaction request. It would only get executed at least exactly once on the actual platform. So the real issue here is that you can't really guarantee anything when the request leaves your own premises. You can have a super reliable system. You can have a supercomputer at your disposal that never fails and never goes down. You can have a really cleverly designed literal action system that makes sure that even though your fleet is comprised of a bunch of imperfect machines, it operates as if it's a single machine that never goes down. But at some point, you're going to talk to external APIs, such as the bank or the payment card provider. And those guys oftentimes would not have these guarantees. With respect to the actual charges and chargebacks, the APIs are pretty robust these days. But every once in a while, you would end up in a situation where at some point, you make a request to the system. And if the system doesn't get back to you with the response, or if the machine that made this request died in the middle, you have no idea if that request was sent there or no. You cannot have this guarantee whatsoever. In which case, the real question is, how much do you care? It's important that you never solve the problem that cannot be solved. You only solve problems that can be solved. So if you have to work with an API that does not have idempotency guarantees, you know that every once in a while, at least in theory, the request can fail. What do? You make requests one by one, have confirmations, and then you can calculate that on average, once in 10 years, somebody from your team would have to pick up the phone and call the bank or whatnot and ask, hey, we've made this transaction with this token ID or whatnot, and we have no idea if it succeeded or if it was even received by your institution. Could you please confirm that? So instead of trying to solve the impossible problem of making sure these issues never happen, you just work around them and commit to potentially involving a human being every once in a while. So sometimes, I'm still going to move these things slightly. Hopefully it's not going to bother us. I'll move it here. Sometimes the problem is real. The standard way to construct a real problem where exactly once is essential is, of course, financial transactions. So let's say I'm going to give you a semi-real example where idempotency is the key. Imagine you have some system that actually runs transactions in a pretty high-performance, high-pace setting, and you have some analytical backend, which is eventually consistent with this system. So this is where the business logic runs. This is where the reports are run, more or less. So there's a replication bus. This analytical system must be eventually up to date with this system. It can be behind by a couple of seconds, doesn't really matter. What matters is that whatever happens in the actual database makes it to the backend, the data warehouse where analytics takes place. So there's going to be a stream of messages, plenty of messages that make sure the state here is identical to the state here. And imagine there's a financial data here, such as there's user balance. So you have Alex, and at some point their balance increases by $100. Maybe they made a deposit. If the message between this system and this system is increase the balance of Alex by $100, then we clearly have a problem. If it's not delivered, then Alex's balance would be lower than it should be by $100. If it's delivered more than once, then clearly it would be $100 times n. So $100 times n minus 1 extra. The standard ways to work around this, again, as in most system design problems when it comes to distributed computing, you don't have to know all this. You can just think of the problem and come up with reasonable ideas, and that's what you're supposed to do in most cases. So there are four kind of obvious solutions down there. One obvious solution is that you don't really send the message that Alex's balance is $100 higher. You send the message that Alex's balance is now $600. So it's plus 100 and it's now at 600. So it was 500. If this request is duplicated on the wire, if this communication channel was laggy and shaking and some component here potentially retransmits the data because it's at least once, not at most once, then, and clearly you don't want to lose messages here. So you have to use at least once. If you have a choice between at least once and at most once, you need to guarantee delivery. And unless you have all these checks and balances to make it exactly once, every single component must be at least once. If something didn't go through, it will go through eventually. Otherwise, your system would break. So at some point you get a message and then you get it again. If the message you get is it's plus 100 and plus 100 equals 600 because it was 500, whether you see it once or 10 times doesn't make a difference. Now, there could be issues that you see it in different orders. Maybe it was plus 100, which is 600, and then plus 50, which is 650. If the order is flipped, then you're in trouble. But that's a second order issue. We'll get to that shortly. It's just, again, in practice, there's the terrible solution is to just send a message that says balance of Alex plus equals 100. The solution that is somewhat better is it's plus equals 100 and now it's 600. In practice, it's a lot better. If somebody sends a message of Alex's balance plus equals 100 and it goes to production, it's a disaster. If it's my top line among these four, the disaster is orders of magnitude smaller. It's still a disaster if you have to replay like half a day of updates, but it's a much smaller disaster. The second obvious solution, again, it's not perfect. I'll get to that in a moment. But the second obvious solution is add a timestamp there. So what this side would see is the balance of Alex should be plus equals $100, and it happened at that point of time. So if this is a time axis, it happens here. Logically, what that means is that if somehow, so on the receiving end, what you would do, you would keep the timestamp of the last update to certain balance. So if you see the update from the past, you just don't apply it, assuming you have already applied this update before. Again, you can see what the issue is if two updates are flipped. So you had updates, some delay, and then these two come in the wrong order. You're gonna apply the second last first, and then the last one is not applied because it looks like it's from the past. So again, suboptimal. The remaining two solutions are actually good. The third one of four is involve transaction ID there. The message would read as in Alex's balance goes up by $100, and this transaction has the ID of whatever. In this case, you can just make sure on the client side to never ever apply the same transaction twice. This makes perfect sense, except one detail. It is kind of important at times. At times it's not, but it's important to understand this detail. This detail is that keeping all these transactions in some hash map or a hash set could be painful. It's a lot of RAM. So in theory, if you cannot have any guarantees on the amount of time or the amount of messages by which your communication channel can lag messages, so can you guarantee it? If you, for example, would say, my system guarantees me that I will only see messages at most, let's say, 24 hours into the past, then you only need to keep the hash map of the last 24 hours of transactions. But if you want to be fully idempotent, you have to keep these transaction IDs until the beginning of time, which is painful. You can get around that with a few clever tricks. You can have transaction IDs prefixed with timestamps somehow, and then you get into all these issues with clock synchronization. And even if the clocks are perfectly synchronized, you never know which communication channel was down. So maybe some part of the internet was down for a while, and then the connectivity is restored. What do? Your caches are now invalidated. So one could say it's not a painful problem. It can be worked around. That's true. It can be worked around. Conceptually, though, it's still the best solution we have. And the last solution, line 4 here, is you send a message that is Alex's balance is now $100 higher,
And this is the balanced revision 123. Usually you would combine these with the previous line. So you have Alex's balance, revision 123. Here's the transaction ID that made it to 123. And here's the one that makes it to 124. So you can always, if you have this whole event log of all these mutation updates, you can always replay it in full. It's going to be perfectly replayable. Every single time the balance of Alex changes, this revision is increased by 1. We are effectively inventing a ledger. It's not a blockchain, but it's close. If you hash every single line of this update, of this mutations array with something from the previous line or previous balance update, you would end up with something verifiable, replayable, which is really close to what the blockchains really do. The real issue here, actually, I'll change the slide and we'll talk from there. So the first two solutions, as we just discussed, are not good. The third one is idempotency. The last solution is suboptimal, which I'll tell you in a moment why. Well, look at the last part. It's always hard to synchronize slides and the live conversations. So let's say the slides are for those who are not here. If you're here, welcome. So the issue with that differentiates the last two solutions that are good, so green and blue, idempotency and ledger, is that it's the very difference between monolithic and microservices architecture. The real question is if you can guarantee that there's a single component, single piece of your architecture, single piece of your pipelines that is making updates, making changes to the balance of Alex. So if you have a single machine or a single cluster, single leader elected set of machines, and only this component is responsible for making changes to the balance of Alex, then this entity can be expected to plausibly enumerate, or as it's called these days, serialize. Not serialize as in binary to JSON and vice versa. Serialize as in put indexes, stamp sequence numbers. So if you have the entity that can stamp sequence numbers to Alex's balance, you're good to go. Because this entity can always guarantee the order is going to produce a perfectly replayable, perfectly ordered set of updates, and no collisions can possibly happen there. The issue is that a lot of times these days, it is really hard to design systems in a way that makes every single mutation to some data entity serializable. As in, you can. So once you can assign, it's really hard to phrase sometimes. Once you can assign the universal order to whatever happens in the system, once you can enumerate that A happened before B and B happened before C, and there's exactly one, the increment of 1 in this snapshot index. So if this is 1, 2, and 3, when you see a 3, you know there is nothing between 3 and 2. It's unique single increment. Once you can afford this guarantee, a lot of things become easier. The truth is, it is really hard to maintain this guarantee. It's almost impossible to maintain it unless you are a single node, or at least single leader elected node. If you're designing a monolithic service, and by the way, it's a huge holy war which we might eventually get to on this meetup. Full disclosure, I'm still a huge fan of monolithic architecture. I see tons of benefits in microservices. I use them, I design them, but I'm still a huge fan of monolith just because you can always give this guarantee. And to me, it matters a lot because I work with data and I work with data streams that are reliable. But once you have multiple teams designing multiple components in different languages with different database, not even different databases, different database paradigms. You have one team that uses Redis for caches, one team that uses Mongo because they feel like they would like to scale up their document storage, one team that uses Postgres, one team that uses Oracle. At some point, it becomes really hard to enforce it on a company scale, on the company-wide architecture. That certain mutations, a certain entity, only all have to go through the same entity when it comes to changing this particular field. It's kind of easy with balances. If you're working in an industry where you do have this financial balance, there's a good chance you have some old school team that owns the component called the wallet, the cashier, the balance tracker, the account manager, or whatnot. And this component is responsible for all financial transactions. And every single new hire would be told, hey, you can build your own things here and there,
But once you would like to make requests to get balance or change balance, you would have to work with that team because those guys and gals know exactly how to do it right. So balance, with respect to this particular exercise, balance is actually something I could plausibly argue that ledger is a better solution than idempotency. So 4/3. But it's only because financial transactions are so critical to the business. Whenever it comes to something like anything that a customer support agent can change. So you have some payment issue, or you have a bonus that somehow you had an issue with the free version before, and you were given a bonus to use a paid version as without paying for the next 12 months. And then somebody calls because it expires, and you want an extension, or you paid with a credit card, and it did go through, but then it was charged back. Whenever you have, and so in order to make you pay in the future, what happens is the service would like to disable some features for you because the product manager on this particular feature set would like to request that only paying customers have access to this feature. Whenever you have anything like this, there's a good chance you would not have a single component doing that. There's a good chance you would not have a single table, a single row, and a single table and a single database that's responsible for that. You would have layers and layers of business logic. And whenever you have this, serializing this in a strictly incremented by one order of mutations is impossible. A lot of people at this point would say, oh, we have microservices and we have some reactive streaming protocols and we have Kafka. So every single mutation is put into this message bus that guarantees increments by one in terms of mutation indexes. That is kind of true, except you have now lost the exactly once guarantee when it comes to put into this queue. What if the machine dies after it performs the operation and before it goes into the queue? Or what if you decide to put into the queue before you make the operation happen, but then you put it into the queue and die before making the operation happen? What if it's multiple transactions in different databases? Your machine crashed because you had a buggy version of software. It has some seg fault between updates 5 and 6 of 10. So things do become tricky there. So the bottom line is, if you can afford to have this serializable sequential by one increments indexes of whatever happens in your system, by all means do it. Your users will thank you. If you cannot afford this, or if you feel like you may be required to break this guarantee sometime in the future, there's a good chance you are better off with idempotency tokens, because in the modern days, hyper-growing companies would grow faster than you can imagine, and they would probably introduce microservices there. They would hire a new team, use a new fancy language, and you would need to be friendly towards these people. That's my view as an architect that has seen these things done right, done wrong, then more wrong. That's painful. Was I making sense so far? Right.
Yeah, sure. And also Lamport clocks, like, is nice to mention here. It's like, if we're talking about the sequence number.
Lamport clocks is one of the awesome papers I totally recommend. It is almost impossible to read. I confessed to reading this only about 2 years ago, even though the paper is, I think, 70-something. Lamport is the guy who invented Paxos. Paxos is impossible to understand. Raft is the modern replacement. That's the leader election protocol. I'm going to shamelessly boast here and give you guys my interpretation of this. Thanks for the question. I almost forgot to talk about this. I have arrived at the way to explain this many years ago, like 5-6 years ago, that I think makes a lot of sense. The way is that if you live in a single-threaded, single CPU, single core world, you live in the Newtonian mechanics. Once you have multiple machines, it's Einstein's, it's relativistic. So the whole idea of simultaneously happening makes no sense. There's no such thing as simultaneous processes unless you are on a single core of a single machine. Even if you're multi-core on a single machine and you use multiple cores effectively, you would still have this issue that you have no idea at which point which core is. And if you imagine for a moment you have a system that is deployed to a data center that has machines across the galaxy, the solar system. So you have servers orbiting Earth and servers orbiting Mars. At different times of year, of different astronomic times, there are different latencies between different servers. So there's no universal time whatsoever. There's no concept of I have this universal time. I'm going to align everything to the time that is measured at this point. Because if you measure time at some point, you have to define the point somehow. Let's say you define the point as data center in Greenwich in the UK, because why not? The latency between this machine and some other machines on the orbit would be different times. So if this is your O and then you have A and B, sometimes A to O is shorter than B to O. Sometimes A to O is longer than B to O. So even if all the clocks are perfectly synchronized, even though even there you have relativistic effects with velocities, even if all the clocks are synchronized, because the communication time is different, you cannot possibly argue that something on A happened before or after something on B. There's no comparison operator. It's compilation error. You cannot possibly compare times here and there. So you have to design the system in a way that can deal with lack of consistency with respect to order of events coming from different sources. From a single source, you can expect you can plausibly expect that when A tells you, hey, while you were away, while the connection was down for a split second, on my machine on A, the following 10 things happened. You can guarantee that on A, within these 10 seconds, the order is fixed. A1, then A2, all the way to A10. There's no way that A5 happened before A7. But between 10 things from A and 10 things from B, you just cannot make any assumptions about their relative order, even if A and B are different cores of your CPU. That's important. And I'm not even trying to make jokes here. Even within the same CPU with the same fixed hardware, there's prefetching, there's hardware hash tables for branch prediction, there's cache warm-up, there's so many things that can go wrong. So if you have multiple CPU, if you have even 2 CPU cores, you cannot know which instructions will be prefetched and pre-run. So not until the moment they freeze the data bus and talk to memory again. That's how data synchronization works within a single machine. At some point, the CPUs have to all stop at some point, and only when they're stopped for a moment, they can synchronize. So Lamport clocks is this fundamental idea that connects computer science and, I would say, philosophy, that you cannot do these comparisons. You can only make certain assumptions. And I've seen people reinvent this all the time. Actually, that's pretty fun to watch how people reinvent the same idea, and then their eyes get so shiny. Oh, I'm onto something. Well, you are, but this is known for a while. Somebody on my team invented this by calling it bitemporal time. So I have like server-side time and client-side time. Oh, I'm going to have a bitemporal index. So I'm going to have client-side and server-side time as a pair. So once I order them, if within one pair of client and server time, both components are less than the other pair, then this happened before this. Otherwise, you don't really know for sure. Well, that's true. It doesn't win you much, but that's true. When you work at this level and the system has high load and so low latency, at some point you have to consciously make the call to not even try to compare things to one another with respect to time. So either you can afford to do serialize time in a fixed 1, 2, 3, 4 order, or you cannot. If you do it right, you can synchronize. You can stamp indexes carefully at the pace of a couple billion per second. I'm not kidding. But if you have to design a system that scales beyond that, or if you have to design a system that works on poor hardware, then at some point you have to make a call that I'm not trying to stamp everything with a specific index. I'm going to design a system in a way that multiple components can run in parallel. And then once they can be run in parallel, they can be different CPU cores, different machines in the same rack, in the same data center, in the same continent, in the same country, different providers, different latencies. So you have to design for that. That's pretty hard, but it's possible. On the unofficial conversation we had on this topic before, this question about how to design transfers from A to B, where A and B are across the continent, across the globe, we had this conversation offline. How can we possibly make transfers between A and B in a reliable fashion? You can come up with clever ideas of how to, if A and B happen to be in the same shard, in the same machine, CPU, rack, data center, continent, planet, within the same rack, you can have a quick transaction, but if it travels across data centers or continents or planets, you would have to put them into some micro escrow special node that physically holds these funds between A and B. So it's first debited and then credited. Both happens exactly once. And then you have to rely on all 3 systems, never losing messages and having idempotency tokens here and there. And maybe some external synchronization that orchestrates when should these steps happen, strictly one after another. That's interesting, fun, and hardly used in practice. In practice, what you would have is, we have this monolith that handles transactions, or we have this microservices, but we have a Kafka bus that handles these mutations and orders them. And it's perfectly fine to live within the realm of existing techniques. It's just important to know the fundamentals of where can things go wrong. When it comes to, let's say, a huge distributed database that you can trust, another one you can trust, and Kafka that you can trust because your team of SREs deploys this Kafka and maintains it. Within these three components, if anything goes wrong, it would be between the blocks. So the application server that changes the database and Kafka on the write side, and then the same on the read side. That's the parts you have to stress test extremely carefully. Oftentimes you would have to reinvent two-phase commit. Oftentimes you would have to put two markers. So I'm starting doing that and I'm done doing that. And you have some backlog audit jobs that would have a big red flag for the SREs in PagerDuty. Hey, I have some inconsistencies, something that was started and not finished. And there would be a semi-manual process of if whatever period of inconsistency is there, you would have some semi-manual process of confirming that, we made one deposit during this time, so we send money elsewhere. Let's call the bank and confirm, because that's the only way to guarantee that. Or you would say, you know what, in this particular case, if I made a mistake on my own side, on my own server, I can pay for it as a business. There's no big deal if I make a lot. If I suffer a loss of a few dozen dollars, I'm not going to invest 2 engine developer years to make sure that the likelihood of this issue goes down from once a month to once in 10 years. It's just not worth the cost. That's how decisions are usually made. It's just important to understand that we have reliable systems and we have custom systems. And custom systems tend to be less reliable. Databases are reliable. Kafka is, I would say, reliable, even though I don't like it that much. Surprisingly, Redis is reliable. Application server that talks to them, written by some junior developers in Node.js, chances are, if I have to look for a bug, I will start there. All right. I think I have one more slide. Oh, actually, I have 2 more slides. So we just started talking about this. Lamport clocks gets us to two-phase commits.
Yeah. About the clock, so there is another clock, I think, called vector clocks. So is there any like different scenarios where we prefer one over the other, or like you can use any of them for any like specific use cases?
I think when I mentioned this gentleman who invented bitemporal time, you can think of the tuple, the pair of times, as the vector of size 2. Vector clocks, if I know the term correctly, I think I do. Vector clocks are if you have multiple dimensions, and only if every single component is less than the other vectors components, you can assume this happens before this. Otherwise, you have to manage them. Yeah, I think it's an interesting standard term, like multidimensional thinking.
Superset of the Lamport clock.
Yeah, two-dimensional Lamport clock. When I heard this term first, I joked about map clocks. You can think of a vector clock where you don't know the number of dimensions up front. So you have arbitrary set of keys that potentially populate as vectors. So that's all sorts of issues. It's easy to imagine a map clock. If you have a data center with, let's say, 100 machines, they all have IDs. So you have a vector clock with a dimensionality being the number of machines. So you deploy this code that runs in production for many years. You're no longer on the team. And then later on you realize that after you left, they added more machines. So the vector dimensionality changed. And then they have an issue with that software, and effectively they do have a vector clock, except suddenly it's different. It's a different vector. It's important to know these terms, to reason about them carefully. But in my experience, how do I put it in the terms that are correct enough to be put on YouTube? In my experience, people tend to split into 2 categories: those who want to know this and those who don't. So if you want to know this, you would know the terms and you would read up and you would reason about them correctly. If you don't want to know about this, just knowing these terms would be sufficient to scare you away. So if you want to learn how to deal with this, just know enough and you'll find yourself talking to people who know this. That's at
Okay.
least that's my experience. So yeah, it's a really good question. Keep asking them, especially to your coworkers who think they have invented everything without knowing these terms. Since we're on this page, I mean, this topic blends a lot of things, even two-phase. So exactly once and two-phase commits are two big topics. They're fairly advanced. Leader elections are also advanced, but somewhat easier. So read up on that. Lamport clocks. Lamport himself talks about the Paxos algorithm. It's hard to understand. I don't claim to. I've read some tutorials and there are some visualizations. Paxos made easy. That's still hard. Raft is the modern day replacement. Consul, etcd, a lot of other things use Raft behind the scenes, under the hood. So this is something that is useful to know. And fundamentally, once I talk about this auto increments, if you even want to make sure you design a system so that every single mutation to everything in your databases, in your set of databases, every single mutation gets an index stamped. So you just want to linearize all the changes. You are okay waiting. You're fine if it's taken slower, but you want to stamp these indexes. This problem alone is almost impossible to solve correctly because you hit the cap theorem. The only thing you can do is have a single leader elected small cluster that sends back the response with the ID for you to use right now. But then what if you die? So you have this single cluster. Let's say I give it an unbreakable machine. Let's say by some magic wand, you have a server that is always up. It has a fixed IP address. You can send a request there. It's going to give you the next number. Even this alone doesn't solve your problem. Because what if your small service requests this next number and dies? How long do you wait? What if your timeout is 5 seconds, but then this service attempts to write in the log at 5 seconds plus 1 millisecond, and it actually made the change in their own database. So this alone is really hard. If you really want to solve this problem, you would need to use some imaginary unbreakable machine, imaginary always up and running machine, that would internally have some state machine. They would at least perform these two-phase commits. So you would talk to this machine by saying, hey, I would like to make this change, and then, hey, I've made this change. So that every single service that you have on your side will be able to roll back every single transaction the same way. And this is as close as you can get. And this is actually where you do get when you use console the right way, when you use leader elected cluster that assigns these IDs the right way. And then the real design problem becomes, do you have this, because leader elected changes are slow. If you want to make leader elected cluster cross cluster, if it's the same shard, it's okay. If it's the same data center, you have this latency of sub-millisecond, of course, but it's still latency. So if you want to synchronize requests back and forth, you have a cap at a few thousand updates per second. If you want to synchronize two data centers like this, and they are, let's say, 1,000 kilometers away, speed of light becomes an issue. So you can only make a few hundred changes per second. So you don't want to use this state machine in the leader elected cluster for every single mutation. So you would need to think about how do you split your state machine into potential nodes, which are surprise microservices. Even if you're a monolithic architecture, this will be microservices in the true definition of the word, because they have their own clocks. By the way, the standard definition of microservice that's often misunderstood this day. People think of microservices as simple components built in other languages with their own databases. That's only part of the truth. The definition of microservice originally goes back to Lamport. Microservice is what introduces the new dimension, the new component to this vector time. If you have multiple microservices talking to one another synchronously and they act with respect to the whole system as a single being, they're not a microservices architecture. They are a well-designed single component. But on the other hand, you can have the same system on the same machine that uses CPUs cores in a way that different cores form different microservices. That's pretty common in financial systems. So you have a super fast system that runs financial transactions. You have some analytical systems that compute some features to power these transactions in high frequency trading. Effectively, on the same CPU, you have 64 cores, and 8 of them are one microservice, and another 20 other different microservices. These systems exist for real. So yeah, the bottom line is, at some point of doing this right, you hit the cap theorem, which means it's impossible to solve this problem precisely unless you really are willing to compromise on throughput. at which point you have to think about exactly this: vector times, conflict resolution, two-phase commits, which is honestly not that hard. All you need to do is to make sure every single component you have has this atomic pause button. So you tell it to work for a while. This while can be seconds or milliseconds or days, and then you synchronize this component state with other component state. And the synchronization happens while this component is read-only for its own purposes, so it cannot make new transactions. And it's, in most systems I'm aware of, it's perfectly fine to have these delays every once in a while. You just need to figure out what the right delay is. I mean, I think even Gmail has this. It's just, if this delay is 5 seconds and it's different times for different data centers, different clusters of different users, the user would not notice. That's how it's done in the real world. Anything else on this topic? I love it, by the way.
A simple idea, but the solution is quite complex.
Yeah, I mean, in practice, the bottom line is that once you can have idempotency tokens, you should be good to go in most cases. One thing I forgot to mention behind the scenes on the previous time we met is that there was a good question: how do you generate those tokens? The simple answer is big random. You would not go wrong with that answer. There's one, and the second simple answer is that you have to persist them. So if you have a system that uses idempotency tokens, the entity that generates this token must put it into the database. And before you start using this token, this database must persist it somewhere else, or at least in memory of other machines. So that if this application server dies and the other one picks up the same task, it needs to be able to get the same idempotency token from the database. Otherwise, it's pointless. So with respect to your application server, there will be synchronous call, or more like a call with a callback to the database. So you generate a token, you put it into the database. Only after you get back the confirmation that it's persisted, you can use it. It's a second simple idea. So one thing I forgot to mention the last time is oftentimes you have some end user action that triggers the mutation. In the vast majority of cases, that's a human doing something. So for example, if it's a financial transaction, you as a human are the initiator of the transaction, right? You're going to use a web server, you're going to use a mobile app or whatnot, SMS confirmation, chatbot, whatever. So one important thing is a potential source of multiple transactions is originating from the client itself. I'll give you a simple example. Sometimes I reply to a Facebook post from the plane, and the plane is already taxiing to be taken off, so the internet is poor. So I finish a comment, I click post, I see it says posted, and I put my phone to the airplane mode to take off. Fairly often when I land, I see the comment 2 or 3 times, which is kind of embarrassing. It's Facebook after all. I mean, can they just make sure that the phone itself keeps the idempotency token? So if the message is sent from the phone to the server multiple times, there is some unique ID that makes sure the same comment doesn't get posted twice. You get the idea, right? One guy I used to work with was asking this as an interview question. How do you make sure the single click in the browser? So you click pay. How to make sure this click does not result in multiple transactions? The answer he expected was that, you know what, in the browser, you can put a JavaScript on click on the button, so you can disable the button after it's clicked the first time. That's a clever answer, but it's an incomplete answer. What you should do is make sure that once the page loads, it gets some request ID prefix or a salt for the hash. If you can go further, and you can make sure that once the page loads from the server sends you this request ID to use for this session. So however many times the request leaves the browser, once it reaches the server, it has this unique ID, and the request would not take place twice. Because again, you have to understand, you never know what's in between the client and the server. If it's on Amazon, behind Amazon load balancers, if it's in a corporate network, there could be some packet inspection tools here and there. You just cannot guarantee that the request reaches the server exactly once. There's no guarantee that even the TCP packet would not hit the client twice. Like that's just how the world is. I mean, you kind of can rely on TCP implementations because it has its own windows and checksums, but that's about it. So if it's the same HTTP request, I mean, I'm fully aware that I think even on Nginx level, for posts, puts, and deletes and patches, it tries to make sure the request doesn't go through multiple times. For gets and heads that are by design idempotent, there's no guarantee that your reverse proxy would not result in a get from the client not hitting the server twice. Because the convention is that it's a GET request. It should not change anything, so it's okay. So, and I've seen people design systems where the actual mutation request from the client side to the server is a GET request with a special nonce in the URL well, GET doesn't have the body. So you can design a system where your change request is HTTP GET, some URL, question mark, whatever. That's an okay design for the prototype. Just keep in mind that in production, there is no guarantee that GET only gets to a server once. At any stage of this flow, whatever entity that receives this request as an HTTP request, not as the transport packet, but like Amazon load balancer. This Amazon load balancer scale, if the load suddenly spiked, it would go to a different machine. Some packets would be lost, and it may send you GET request twice. Even if it's not the case with Amazon load balancers, it likely is the case with other data providers. So don't trust it. Put your own tokens there. That's important. The bottom line is that I would like to amend to what I said before, off the record, that when you generate idempotency tokens, large is important so that no collisions can happen. Persistent is important so that if the other application server has to pick up it where you left, it uses the same token for the same operation. And consideration number 3 is you probably want to generate them as close as possible to where the actual user that prompts the action interacts with the system. At which point, by the way, you get back to the clock synchronization. So you could say something like, oh, when I'm interacting with my social media platform, let's say, that's actually a real design of the API. No kidding. That the backend gives the phone app a new token every, let's say, 10 seconds. And the app is expected to use the token issued within the past 15 or 20 seconds. So the app was offline. If you're in a train, the train enters a huge tunnel, happens in Europe, and then you try to do something from within this tunnel, and you leave the tunnel, and that was like 2 minutes. You could design the API so that it would not accept the request with the authentication nonce it has received 10 minutes ago. The app itself, the client-side logic on your phone would retry the request, but it would retry it only after it hears back from the server, hey, I know you're logged in, I know you're online, here's the new token that is valid for the next 10 seconds if you would like to change anything. This way, it's a bit easier to align this Lamport clocks, vector clocks, because this way, once you have this trace ID, request ID in your system, you can provide stronger guarantees that if something happened in this time, the request ID should be prefixed with the timestamp that is not too far off, single-digit seconds off. And single-digit seconds is something you can guarantee in terms of time synchronization between machines. Single-digit milliseconds is really hard. Single-digit seconds, doable. NTP does that for you. So tons of mixes of theory and practice. I hope most of us don't have to deal with this in the real life. In practice, just knowing the fundamentals does the job. But trust me, once you start digging here, it's turtles all the way down. All right, what did we miss? Yeah, that's the last slide. Let me just summarize this. Use idempotency tokens, persist them, tie them to the user. Keep in mind it's impossible to guarantee pure exactly once unless you own the whole system, and even in those cases, it's fairly tricky. Don't try to solve the problem that should not be solved. Instead, run the cost-benefit analysis. And if at some point you realize that your system is robust enough, and even if something goes really wrong, what you lose is single-digit dollars, more or less, for the company, or maybe single-digit thousands of dollars. It's not worth engineering years of development. And in theory, there's no difference. In theory, there's no difference between theory and practice. In practice, there is. So if something goes wrong, look at the practice first. And the practice is that it's like with compilers. Sometimes there are bugs in compilers. I've known people who had issues with their own code because they found a bug in the compiler, but it's highly unlikely. So if you use a multi-tenant distributed reliable database with RAID clusters on the one side, with good DBAs that guarantee your data consistency, and then the same on the other side, and then you have a Kafka cluster in between that is managed by the team you trust, and something goes wrong, most likely this something that went wrong is in the connections between the first database and the Kafka writer, or the Kafka reader in the second database. Look there. Stress test these things intensely. By the way, yeah, there are tons of ways. Another important topic, maybe one of the last ones today. When you stress test, it's important to stress test these time nonlinearities. In my own code, what I do is I actually put markers in the code. That this is where the delay can take place. So when I run the stress test, I instrument the code where my code is rebuilt with the markers being replaced by arbitrary delays. And arbitrary means exponential distribution. Could be a millisecond, could be 10 seconds. So that it's not the best test, but it's about as good as you can get when it comes to making sure different orders of execution are tested. Because at some point, your machine will be overloaded. You'll be out of RAM and it's going to start swapping, or it's going to be Windows Update because you use a Windows server for whatever reason. A lot of things can go horribly wrong, and you have no idea which part of your code will suddenly get slower. And a lot of issues, you would just not see them with your own tests, no matter how long do you run them for, unless you explicitly make assumptions that certain atomic-ish operation can suddenly take a lot longer than you expect. So that's why I put those markers everywhere. Proper testing of large systems is another huge topic. It's nearly impossible to test everything. But at least make sure that once you run tests overnight under high load, put arbitrary delays from an exponential distribution. So that you at least you can sleep slightly better knowing that whatever can possibly take more than you thought was likely tried in this setup. You would often be surprised. I think that's all I had.
Sorry, could you repeat, please, about exponential delays? I don't got it.
So you have a piece of code
Yeah.
that performs multiple operations. And it's multi-threaded or multi-machine. So multiple pieces of code like this can run on multiple machines. Let's say you have 10 operations. So you have 9 delays between them. Every single time of these 9 can possibly be stopped for any amount of time, any being 0 time or 10 seconds. So in a perfect test, so look, how do I put it? I think most of you are familiar with microservices. So you have the graph of states of your system, and you have edges that denote how can the system change from state A to state B.
The probability of change.
Right. I think it's an umbrella term. Yeah. In data science, it's a probability, and you have a stable equilibrium and all that stuff. In mass consumption theory, or whatever it's called in English, there are other things. That's, for the record, my master's is in this space. It's really interesting. So the thing is, microprocessors are fairly simple, and there are Petri nets. You probably have heard of them too, Pooja, since you know this stuff well. So it's when you have multiple, instead of a single state being the current state, you have multiple balls traveling through this graph. And you can have balls of multiple colors with their own different probabilities. The point is, once you have multiple balls, once the state is multidimensional, your whole graph explodes exponentially. So if you have a single CPU, single state machine, however many states you have, however many state transitions you have, you can just run the test. You can implement the test that makes sure every single state transition was tested.
Mm-hmm.
It's another thing. What to think about this is code coverage. We all know that code coverage in unit tests means nothing, right? So I can come up with a simple example where you can test the code with 100% code coverage and it would not find a bug, because the hidden state is concealed with some variables that have unexpected mutual conditions, and it looks like every single line of code was executed. But the bug exists because this line executed along with this line, whereas they must have been this or that. So just 100% green doesn't mean anything. So once you have a single core software, you can, whatever the delay is between two steps is immaterial. Once you have multiple cores or multiple machines, the relative order of them can be anything. So the idea of arbitrary delays is that you increase the likelihood of every single order potentially occurring in your test setup. So a lot of people agree these days that you have to run stress tests. So you come up with a beefy machine, or you even spin up the whole new cluster for testing purposes. The company pays tons of money, you spin up 100 machines because you have Kubernetes, and you run the same test. That's a healthy thing to do. But if you do it without introducing arbitrary delays, there's a huge chance that you have like 5-tier process for 4-tier process, and maybe it's like two operations, and they're super fast with one another. And then the other one like works like this. You can have a 99.9% chance that you would have this, and this. But you would never have this, statistically. Once you introduce arbitrary delays here, you increase the chance of your stress test actually hitting that code path by orders of magnitude. And that's why bugs tend to hide. I don't think I could explain this better within a few minutes.
Yeah, I got it. Thank you.
Good questions, Fox. Keep it coming.
Yeah, so I have a question. So if we are using idempotent tokens, do we need two-phase commit? Maybe my use case is different and I don't need acid. Like I'm fine with eventual consistency, but it can be at least once as well, right? So in that case, if I'm tying the idempotent token with the client, I don't really need two-phase commit, right? Let's say I like someone is liking my post and I want to increase it. It can be eventually consistent, but I want it only to get incremented once for that user. So that is also one use case, right?
The issues emerge when you have multiple pieces of data to synchronize. So when something went wrong, if it's just a like in a single table, you should be good. If you have to make changes in multiple places and potentially revert them, if the condition failed somewhere, then at some point you will have to re-implement the whole revert logic, because it may also be cross-service, cross-machine. It will have its own second-order tokens reissued. So yeah, that's important, by the way.
Yes,
I've done
that's like more related to transactional guarantee, right? Like when we have multiple machines and we want to synchronize.
Right. And by the way, in that case, so the request comes in, and you have multiple operations to perform. It's weird because I'm showing left to right to you, and I just realized that on the video it's actually right to left. So what happens is, if your operation expands to multiple operations, then what you can do, and what you should do, by the way, because these multiple operations are predictable with respect to what would trigger what, your idempotency tokens with those sub-operations can be derived from your first token. So you can have the original token You can put like, if it's a string, you can put dash something. With this something being fixed as a fixed function of the state of what's happening within your own thingy. That's healthy, that's normal, that's what you can do. But again, the trade-off is, do you want to implement your own custom rollback logic? If you can do it, then idempotency is the way to go. So the question really becomes, what do you couple together? That's another meetup I would like to do on the value of SQL. I used to hate SQL, now I love it because I know how powerful it is. So SQL, in a nutshell, has multiple values for the customer. One of them that's often overlooked is the power of transactions. The transactions that are, so it's incredible how much work the SQL database developers have done 20 plus years ago to actually implement isolated transactions. That's tremendous, that's huge. So at some point, you actually want to rely on that because it gives you so much flexibility. It's so much power. I mean, ultimately, in all systems, what you want to optimize is time to market. You would like to use fewer developer hours to ship more features. So yes, you can use idempotency tokens, and you can just ignore exactly once, ignore two-phase commits, as long as you can roll back every single change on your own. But if you're making one change, it's trivial. If you're making 2 changes, it's trivial. If you're making 10 changes, then suddenly you end up in the world where custom rollback logic is so heavy that you actually want to have a single component that does all these steps simultaneously, and you want to have a database that guarantees that this change can happen atomically. Again, in practice, it's a lot easier. Again, theory and practice, right? In theory, it's hard. In practice, you would say, hey, balances, just shard them by user ID, model or something, and it's done. Content, well, just shard it by location and you're done. And at some point, you have some operation that affects multiple users or multiple pieces of content, at which point you say, you know what, it's fine if I block the whole thing for a split second because these operations are so rare. And it's just so much pain to work with those. And I can give an example. I shouldn't talk about what happens in my company for real, but as a simple example, there are small transactions, financial transactions, and there are large buyouts, large payouts because some tournament has ended or some big event takes place. And to do it right, with no downtime, with no lags, with no lock-in, is really hard. But in practice, you can always relax some constraints. Like if you want a poker tournament, you don't care if the money lands on your account right now or 5 seconds later. But somehow in practice, the latter is a lot easier than the former. So you just make the decision to do something like that.
Yeah.
So yeah, by the way, I think it's safe to confess that this is by far the most interesting meetup I've had so far. I guess the topic was just amazing. So let's take the rest offline because things might change. And thanks everyone. I'm going to stop the recording.